we are starting problems of NCERT textbook that are given in exercise. So the first problem will solving here. Before it, I will tell you one thing. These solutions are for students who are already tried these problems in their own way, and the solutions can be used as reference. There is no intention behind these solutions to replace the classroom coaching and any other standard solutions. So find your own solution, and after this you can get the solutions here. So we're starting this problem. This is a problem, fill in the blanks. The volume of a cube of side 1 centimeter is equal to dash 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 meter cube. We have to find answer in terms of meter cube. Volume is given as cube of the side, where side is given as 1 centimeter, that is equal to 10 to the power minus 2 meter. So volume will be 10 to the power minus 2 meter cube, that is 10 to the power minus 6 meter cube. So our answer is 10 to the power minus 6. Let us see next problem. The surface area of a solid cylinder of radius 2.0 and height 10.0 centimeter is equal to blank with millimeter square. Answer must be given in millimeter square. Let us find first the surface area with appropriate significant digits. Surface area of the cylinder has two parts. One, the surface area of the curved surface, and another surface area of the two plane surfaces. This gives us 2 pi r into height plus 2 pi r square. If we calculate 2 into pi number of significant digits can be taken as 3 here, because there is 2 significant digit in this quantity, and so is given as 2.0. so we have to calculate up to 1 more significant digits if possible, and height is given as 10.0 centimeter. The answer will be 125.6 centimeter square plus 2 pi r square. 2 into pi is 3.14, r square is 4.0. On calculating up to 3 significant digits, and this will be 25.0. On adding these two, we'll get up to 3 significant digits, will only get 150 centimeter square. To change in it to millimeter square, we must know 1 centimeter is equal to 10 millimeter. So this will give us 150 into 10 millimeter square. That will be 1.5 into 10 to the power 4 millimeter square. The answer will be 1.5 into 10 to the power 4. A vehicle moving with a speed of 18 km per hour covers dash 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 meter in 1 second. That we have to find the speed in terms of meter per second. So convert kilometer into meter and hour into seconds. So it will give us 18 km per hour. 18 km, that is 1000 meter, and 1 hour is equal to 3600 second. Now on cancellation, it will give result in meter per second. It will be 5 meter per second. So answer is 5 meter in 1 second. The last part of the problem is D. The relative density of lead is 11.3. Its density is given in per gram per centimeter cube or kilogram per meter cube. Let us know about relative density. Relative density is density of the material divided by density of the water, where density of the water is given as 1 gram per centimeter cube or 1000 kilogram per meter cube. So density of the material will be given as density of the water into relative density. It gives as density of water is 1 gram per centimeter cube into relative density is given as 11.3. So it will be 11.3 gram per centimeter cube. It is clear here relative density has no dimension. It is a dimensionless constant. And also you can write this in terms of 10 to the power 3 kilogram per meter cube. Because if we choose density of water as kilogram per meter cube, it will be 10 to the power 3 kg per meter cube into 11.3. Then this will be the answer. Problem number 2.2. Fill in the blanks by suitable conversion of units. 1 kg meter square second to power minus 2 to be converted to gram centimeter square second to the power minus 2. 1 kg meter square second to the power minus 2. 1 kg is 10 to the power 3 gram, while 1 meter is 10 to the power 2 centimeter, and second is as same, gives us 10 to the power 3 gram. Square of this unit is there, so it will be 10 to the power 4 centimeter square and second to the power minus 2 as such. And this is our answer, 10 to the power 7. Now 1 meter is how much light years? 1 light year is equal to 9.46 10 to the power 15 meter. That is equal to distance traveled by light in 1 year. Light divided by 9.46 into 10 to the power 15. So it will give 1 meter is equal to 1 upon 9.46 into 10 to the power 15 light year. So 1 meter will be, this will be 10 to the power minus 15. This will be 1 upon 9.46. So you can write it as 10 to the power minus 16 and 10 upon 9.46. This will be slightly more than 1, but we can take only one significant digit, so it will be 1 into 10 to the power minus 16 light year. Next part is 3.0 meter per second square is equal to how much? Kilometer and hours to the power minus 2 meter and kilometer. So 3.0. In place of meter, we will write 10 to the power minus 3 kilometer. In place of second, we will write 1 upon 3600 hour. So it will be 3.0 into 10 to the power minus 3 kilometer, that I will write here, and second will be written as 1 upon s square, that is second square will be written as 3600 square upon h square. So unit is comes out to be kilometer per hour square, and we have a number up to 2 decimal places only. So it will give us 3.6 into 3.6 into 3.0, that is 38.88. That is 38.88. There are 6 zeros here and 10 to the power minus 3 here. So it will 10 to the power 3 kilometer per hour square. To get only 2 significant digit, we will write it 3.9 into 10 to the power 4, and this will be our answer. So next part is D. Universal gravitational constant G is given as 6.67 into 10 to the power minus 11 Newton meter square kilogram to the power minus 2. We have to find its value in terms of the unit centimeter cube, second to the power minus 2, and gram inverse. We'll find Newton first in terms of meter and kilogram and second, because we know about the meter and kilogram already well. That is 1 kg is equal to 10 to the power 3 gram. 1 meter is equal to 10 to the power 2 centimeter, while 1 Newton is equal to 1 Newton is 1 kg per second square. So it will come out, so it will be 10 to the power 3 gram into 10 to the power 2 centimeter per second square. That is 1 Newton will be equal to 10 to the power 5 gram into centimeter into divided by second square. So writing the values, 6.67 into 10 to the power minus 11. Newton is comes out to be 10 to the power 5, and I will write unit here, gram centimeter per second square. This is for the Newton. Then meter square, that is square of this, square of 10 to the power 4 and centimeter square. Now kilogram to the power minus 2, that means we have to inverse this here. That will be 10 to the power minus 6 and gram to the power minus 2. G comes out to be 6.67 into 10 to the power minus 11 into this all, that is equal to 10 to the power 3 gram inverse, second to the power minus 2 obviously, and centimeter square and centimeter, that is centimeter cube. Now answer is comes out to be 6.67 into 10 to the power minus 8 cm cube, second to the power minus 2 gram to the power minus 1, and this is our answer. So you can do like this. It is very easy if you remember very simple steps. Let us say this problem. A calorie is a unit of heat or energy, and it equals about 4.2 joule, where 1 joule is 1 kg meter square second to the power minus 2. Suppose we employ a system of unit in which the unit of mass equals alpha kg, the unit of length equals beta meter, and the unit of time is gamma second. Show that the calorie has a magnitude 4.2 alpha to the power minus 1, beta to the power minus 2, and gamma square. In terms of the new units, let us see that 1 calorie is equal to 4.2 joule. That means equal to 4.2 kg meter square second to the power minus 2. In the new system of units, while we know that U2 is given as alpha kg and beta meter square, also gamma second to the power minus 2. Now N2 will be 4.2 divided by alpha, that is alpha to the power minus 1, divided by beta square, that is beta to the power minus 2, divided by gamma to the power minus 2, that means gamma square. So we have got the N2, that is the required magnitude in terms of the new unit, that is equal to U2. That is equal to U2. So let us see next problem. We are including this question now. A new unit of length is chosen such that the speed of light is v. What is the distance between Sun and Earth in terms of new unit if light takes 8 minutes and 20 seconds to cover this distance? Speed of light then will be 1 unit, that is 1 unit per second. In the new unit system, distance traveled by light from Sun to Earth in time 8 minutes and 20 seconds. We'll convert first it into the seconds. 8 into 60 plus 20. It is 480 plus 20, that is 500 second. Then distance will be c into time, where c is new unit per second into second, that is equal to 500 units. Let us see next problem. Which of the following is the most precise device for measuring length? A Warrior caliper with 20 division on the sliding scale. Let us find precision of this instrument first. It will be 0.1 upon 20. That is equal to 5 into 10 to the power minus 3 meter, 5 to the minus centimeter. In second case, precision will be a screw gauge of pitch 1 millimeter and 100 divisions on the circular scale. The precision will be, that is 10 to the power minus 3 into 10 to the power minus 2 meter, that is 10 to the power minus 5 meter. It will be 5 into 10 to the power minus 5 meter, and this is 10 to the power minus 5 meter. An optical instrument that can measure length to within a wavelength of light. Common wavelength of light is about 5000 angstrom. That is equal to a wavelength of light. And it is equal to 5 into 10 to the power 3 into 10 to the power minus 10 meter. That is 5 into 10 to the power minus 7 meter. Simply, this is our answer, which is most precise. Let us see next problem. A student measures the thickness of human hair by looking at it through a microscope of magnification 100. He makes 20 observations and finds that the average width of the hair in the field of view of the microscope is 3.5 millimeter. what is the estimate on the thickness of hair? The average value is 3.5 millimeter, which is very near to the true value, as we know according to rule of errors. And a magnification 100 gives information that and a microscope gives linear magnification of 100, so size is increased by 100 times. So thickness of hair will be 3.5 035 millimeter. These have two significant digits. Also, these have two significant digits. So we have to work up to only two significant digits. Answer the following. You are given a thread and a meter scale. How will you estimate the diameter of the thread? Let us answer this question first. If you have a meter scale like this, you have to make a spindle on the thread on the scale like this. You have to count this number of turns and the measurement between these two last ends. You'll get diameter as the measurement. Suppose this measurement is x divided by number of turns. So this is the answer of part A. Part B. A screw gauge has a pitch of 1.0 millimeter and 200 divisions on the circular scale. You think it is possible to increase the accuracy of screw gauge arbitrarily by increasing the number of divisions on the circular scale? The accuracy is already depends upon 200 divisions. Increasing definitely increase the accuracy on the paper, but not actually will increase, because every instrument has their own instrumental error. Like in a screw gauge, you will find back lag error, and so there are many errors are also possible. So up to one level, number of divisions is appropriate. After that, the errors will make it insignificant. So it is not possible to increase its accuracy arbitrarily. The mean diameter of the thin brass rod is to be measured by a vernier caliper. Y is a set of 100 measurements of the diameter expected estimate, then a set of 5 measurements only. By measurements, we are reducing errors. By increasing the number of measurements, we are increasing the errors, because errors comes in random in nature. Sometimes it becomes positive, sometimes it becomes negative, and ultimately the sum will becomes less and less. To get a better expected estimate, we must take more and more measurements in an experiment. The photograph of a house occupies an area of 1.75 centimeter square on a 35 millimeter slide. The slide is projected onto a screen and the area of the house on the screen is 1.55 meter square. What is the linear magnification of the projector screen arrangement? This is the area on the slide, and this area is now become 1.55 meter square on the projector screen arrangement. That is the area on the screen. So magnification, linear magnification is the under root of area magnification, or say aerial magnification. So we'll find aerial magnification, that will be equal to 1.55 meters square, that is into 10 to the power 4 centimeter square, divided by 1.75 centimeter square. This cancels out and it gives the value of 8857 point something, but we'll take only 4 significant digits because we have 3 significant digits here, and this type of calculation we always take one more digit than the least significant digits in the numbers. So linear magnification will be under root of 8857, that will be 94.11 and so on, but we'll take only 3 significant digits here. So the answer is 94.1. State the number of significant figures in the following. 0.007. These two zeros are not significant because these are on right side of the decimal and left side to the first non-zero number. So significant figures is 1 in case of A. Here significant digits are 2, 6 and 4. So significant digits equal to 3. In this case significant digits are 4, 2, 3, 7, 0. All these are significant digit. This 0 is also significant because in a number with decimal point, trailing zeros are significant. So this 0 is significant. 2, 3, 7, 0. 4 significant digits are here. In this case, this is also a number with decimal point, and there is 1 0 is also trailing here, but it is significant also. So 4 significant digits are here. Now 6.032. Clearly these 4 digits are all significant. This 0 is between 2 non-zero digits, so it is significant. While here these 3 0 are also not significant because it is on the right side of the decimal and total number is less than 1. So there is no any non-zero digit on this side. First non-zero digit is here. First non-zero digit is 6. Zeros are on the left side on the 6. So these 3 zeros are not significant. Only these 4 digits are significant. So we are on the answer. The length and thickness of a rectangular sheet of metal are 4.234 meter, 1.005 meter and 2.01 centimeter respectively. Give the area and the volume of the sheet to correct significant figures. I will say area to be calculated is only surface area, not whole the surface area that is below the surface of the sheet and on the side of the sheets. So I will include only this area in my answer, while in the answer in CBSE NCERT book is different. That is all the area of that, and that area is also correct, but I will calculate this area. This is L into B. L into B is the area, that is 4.234 into 1.005. If you calculate this, it will be 4.25517, but I am including up to 4.2551. If you write only area, that is L into B, you have to use only 255 after the decimal. That you have to use only 4 significant digits, and this will be your answer. If you want to find volume, in case of volume, you have to use 5 significant digits here. In case you are going to find volume, you have to use 4 significant digits here, because you have 3 significant digits in this case and 4 significant digits in this case, so you can use one more digit here. Unit here will be meter square, while unit here will be meter square, and 2.01 is meter, so you have to use 10 to the power minus 2 meter as well. So the answer will be 8.55 into 10 to the power minus 2 into meter cube. That is meter cube. So answer is correct up to 3 significant digits. You have to take only 3 significant digits here only. The question is quite simple, just to take care about the significant figures. The mass of a box measured by a grocer's balance is 2.300 kg. 2 gold pieces of mass 20.15 gram and 20.17 gram are added to the box. What is the total mass of the box? The difference in the masses of the pieces to correct significant figures. Let us add total mass. That will be in the grams, it will be 2300 gram. There are 4 significant digits here, plus 20.15 gram plus 20.17 gram. The answer will be 2340.32 gram. But number of places after the decimal point, here is 0. Here there are 2 digits after the decimal point, so we can use only 2, 3, 4. To find the difference, it will be equal to 20.17 minus 20.15. That will be 0.02 gram. Here there are 2 places after the decimal, and here also must be 2 places after the decimal. So this is the correct answers. A physical quantity P is related to 4 observable A, B, C and D as follows. P is equal to A cube B square upon under root of C into D. The percentage errors in the measurement of A, B, C and D are 1%, 3%, 4%, 2% respectively. What is the percentage error in the quantity P? The value of P calculated using the above relation turns out to be 3.763. To what value should you round off the result? First, the percentage error formula gives us the information, that is percentage error in P will be equal to 3 times percentage error in A, because power of A is 3, 2 times percentage error in B, plus half times percentage error in C, plus percentage error in D, because the power of D is 1, power of C is 1 by 2. Errors are always added, so percentage error 3 into 1 plus 2 into error in B, 2 into B, that is 3 into 2, 6, half into error in C, that is 4 by 2, that is 2, and percentage error in D is 2 also. So this is 13%. Finally, it is 13%. The first answer is this. If the value of P calculated using the above relation turns out to be 3.763, to what value should you round off the result? If you calculate the error, here 13% of 3.763 will be about 0.48. So the quantity will be 3.763 plus minus 0.48. We'll write it as 3.763 plus minus 0.5. That means 7 is now the uncertain digit. So we'll leave all these two digit. 3 is the reliable digit. So uncertain digit will be rounded to 8. The answer will be 3.8 plus minus 0.5. So result will be 3.8 plus minus 0.5 if we show total result, but rounding will give us 3.8. A book with many printing errors contains 4 different formulas for the displacement y of the particle undergoing a certain periodic motion. Y is equal to a sine 2 pi t by t and so on. A is equal to maximum displacement of the particle, that A is the amplitude. V is equal to speed of particle. T is equal to time period of motion. Rule out the wrong formulas on the dimensional grounds. If you see on the dimensional ground, Y is the displacement, A is also displacement, but sine 2 pi t by t must also be examined. Sine 2 pi t by t. This is dimensionless. So it is the correct expression because sine, tan, cos, exponential or log must have a dimensionless quantity. V into t, that is L by t into t, which is not dimensionless. Not dimensionless. So this is the wrong option. A by t. T means displacement upon time, and this should be also dimensionless, t by a, which is not dimensionless here. Time upon length is not dimensionless, so this is another wrong option. Y is a root 2. A root 2. A is displacement, and sine 2 pi t by t plus cos 2 pi t by t also dimensionless. So this formula is also correct on dimensional grounds. The wrong formulas are already found. A famous relation in physics relates moving mass m to the rest mass m0 of a particle in terms of its speed v and the speed of light c. This relation relativity due to Albert Einstein. A boy recalls the relation almost correctly but forgets where to put the constant c. He writes m is equal to m0 upon 1 minus v square to the power 1 by 2. Guess where to put the missing c. In order to find the dimensional analysis, let us do a dimensional analysis of the formula. M is the mass, so here should also be the mass, which is there. Mass is equal to mass. So this 1 minus v square to the power 1 by 2 should be dimensionless. But what I see, v square, which is speed of moving mass, is not dimensionless. So let divide it by c square. May ask why it is not c square by v square. Because c square by v square is greater than 1. Speed of light is always greater than any matter. So 1 minus v square by c square will be negative. Negative to the power 1 by 2 is not possible. So keeping v square by c square less than 1, which gives positive in this under root sign. So this will be the correct answer. You always remember, with the help of this magnitudes and dimensional analysis, you can find where to put the proper physical quantities. The unit of length convenient to the atomic scale is known as an angstrom, and it is denoted by 1 angstrom is 10 to the power minus 10 meter. The size of the hydrogen atom is about 0.5 angstrom. What is the total atomic volume in meter cube of a mole of hydrogen atoms? Let us found value of volume of one H atom. That will be 4 by 3 pi. If 0.5 angstrom is the diameter, then we will take 0.5 by 2 r as r, and its cube will be here. I know the radius of hydrogen atom is 0.5 angstrom, so I'll take 0.5 angstrom as the radius, so it will be angstrom cube. Let us find the value here. It will be 0.52 angstrom cube. To find total volume, multiply it by Avogadro number, that is number of particles in a mole, 0.52 angstrom cube. That will be 3.1 into 10 to the power 23, and 1 angstrom will be replaced by 10 to the power minus 10, then it will be 10 to the power minus 30 meter cube. So we have to take only one decimal place. We have to take only one significant digit, so it will be nearly 3 into 10 to the power minus 7 meter cube. This will be the answer. 1 mole of an ideal gas at a standard temperature and pressure occupies 22.4 liter molar volume. This is the molar volume. What is the ratio of molar volume to the atomic volume of a mole of hydrogen? Take the size of hydrogen molecule to be about 1 angstrom. Why is this ratio so large? 1 mole hydrogen will occupy a volume 3 into 10 to the power minus 7 meter cube, that we already done in the last question. Atomic volume, I will say it, while the molar volume is 22.4 liter. 1 liter is equal to 10 to the power minus 3 meter cube. 1 liter is 10 to the power minus 3 meter cube, because 1 liter is equal to 10 to the power 3 centimeter cube, and 1 centimeter cube is 10 to the power minus 6 meter cube, and so 1 liter will be written here as 22.4 minus 3 meter cube. Let us find a ratio of these two. 22.4 into 10 to the power minus 3 meter cube. Required ratio is this: 22.4 into 10 to the power minus 3 divided by 3 into 10 to the power minus 7. This will be about 7 into 10 to the power 4 nearly. So why is this ratio so large? Because there is interatomic distances. In a gas, there are interatomic distances very large compared to their size. Let us see next exercise. Explain this common observation clearly. If you look out of the window of a fast moving train, the nearby trees, houses, etc. move rapidly in the direction opposite to the train's motion. But the distant object, hilltops, the moon, the stars, etc. seem to be stationary. In fact, since you are aware that you are moving, these distinct objects seems to be moved with you. Let how things appear to us. If we are moving in this way, and this is the tree. If we reach here, the angle made by this position on the tree will change by a significant value. While if you see distinct objects, the angles becomes smaller and smaller if this quantity is far and far from you. So this makes a change in their position with respect to us, and this will seem to be stationary because the angle subtended by these two positions will become almost negligible when these things are very far, like a star or a moon. So this object seems to be stationary with respect to us. In fact, it looks like that they are moving with us because the angle will change by a very small value, almost negligible, and in this first case it changes by a very big amount. The principle of parallax in section 2.3.1 is used in determination of distances of very distinct stars. The baseline AB is the line 6 months apart in its orbit around the sun. Let us reproduce it again. Say this is the sun and this is Earth's orbit. These are two positions of Earth between these 6 months, and this is the line AB. The baseline is about the diameter of the Earth's orbit, 3 into 10 to the power 11 meter. Here AB is 3 into 10 to the power 11 meter, obviously. However, even the nearest stars are so distinct that with such a long baseline, they show parallax only of the order of 1 second of arc or so. A parsec is a convenient unit of length on the astronomical scale. It is the distance that will show a parallax of 1 second of arc from opposite end of a baseline equal to the distance from the Earth to the Sun. How much is a parsec in terms of meters? So this is a star, suppose. So if this star, and this is the angle theta made by the star on the distance between Sun and Earth, this is defined as 1 parsec, and this is half the 3 into 10 to the power 11. When theta is in degree, we have to convert into the radian, and it will be 1 by 60 minute. This is 1 by 60 minute. Now it becomes 1 by 60 degrees. Now 1 by 80 into pi, it becomes radians, and this is the value of theta in the radians. That will be equal to AO, that is the arc upon parsec, the radius. 1 parsec will be equal to OA into 60 into 60 into 180 upon pi, where OA is 3 into 10 to the power 11 by 2, and it comes out to be nearly 3 into 10 to the power 16 meter, and this is the answer. This problem, the nearest star to our solar system is 4.29 light years away. Sun is but next nearest star is Alpha Centauri. How much is this distance in terms of parsecs? How much parallax would this star named Alpha Centauri show when viewed from two locations of the Earth 6 months apart in its orbit around the Sun? Let's first convert light years into parsec. 1 light year is equal to 9.46 into 10 to the power 15 meter, while 1 parsec is equal to 3 into 10 to the power 16 meter. And this distance, suppose D is 4.29 light year, is equal to 4.29 into 9.46 into 10 to the power 15 meter divided by 3 into 10 to the power 16 meter. It becomes parsec. That is equal to 1 parsec. So the value of D is comes out to be 1.32 parsec. And next, how much parallax would this star show when viewed from two locations of the Earth 6 months apart in its orbit around the Sun? We know that 1 parsec is the angle subtended from a distance 1 parsec to the radius of Earth and Sun orbit. But 6 months apart, it will subtend double the angle. If this is theta, this is again theta. If this distance is 1.32 parsec, so this angle is 1, theta is 1 second when this distance is 1 parsec, as we seen just before this problem. And these 2 theta will become 2 theta will be equal to 2 second. But if the distance is 1.32 parsec, angle will be angle subtended by alpha century will be simply 2 second divided by 1.32. The answer will be 1.51 second. While the answer in NCERT book is double of that, 2.64, which is wrong. So this answer is correct, while answer given in NCERT is wrong. As we know, as this distance increases, angle will decrease. Simply, if this distance increases, angle will decrease. So divided by increased distance, you will get decreased angle. This is very simple calculations here. You can do it by more precisely, take it 1.32 and the distance is all that. So learn how to calculate like this. The Sun is a hot plasma with its inner core at a temperature exceeding 10 to the power 7 Kelvin and its outer surface at a temperature of about 6000 Kelvin. At these high temperatures, no substance remain in a solid or liquid phase. In what range do you expect the mass of the Sun to be? In the range of densities of the solids and liquids or gases? Check if your guess is correct from the following. I guess it will not be in the range of gases because of very high gravitation. It will be in the range of liquid or solid. So let us calculate the density. Density is mass by volume. Mass of the Sun is given as 2.010 to the power 30 divided by volume is 4 by 3 pi into 7 into 10 to the power 8 cube, that is r cube. The answer will be about 1.4 into 10 to the power 3 kg, which is the density of liquids and solids. Let us see this problem. When the planet Jupiter is at a distance of 824.7 billion kilometers from the Earth, its angular diameter is measured to be 35.72 second of arc. Calculate the diameter of the Jupiter. First, we'll see that theta is arc distance between Jupiter and Earth. Now the arc is like diameter and distance we have given, but angle we have to convert into radians. So the diameter is the diameter will be distance into theta in radians. So diameter will be equal to distance, that is 824.7 into 10 to the power 6 million, that is into 3 meters, that is million and that is kilometers, into angle. Angle is now have to be converted into, now second by 60 it becomes minute, again by 60 it becomes in degree, again pi into 180, now it convert to the radian. To convert degree to the radian, we have to multiply it by pi by 180, so it becomes now the radians. If you calculate this, you will find 1.429 into 10 to the power 5 kilometer. We are not going through the calculations here because calculation is not the problem, but the concept is more important here. Let us see this problem. A man walking briskly in rain with speed v must slant his umbrella forward, making an angle theta with the vertical. Student derives the following relation between theta and v. Tan theta is v and checks that relation has a correct limit as v tends to 0 as theta tends to 0 as expected. We are assuming that there is no strong wind and that the rain falls vertically for a stationary man. Do you think this relation can be correct? If not, guess the correct relation. First, this relation cannot be correct because tan theta is always a dimensionless quantity while v has a dimension length by time. So this is incorrect relation. While assuming that v tends to 0, theta tends to 0 is the correct thing, this is not true by the dimensional analysis. The correct relation will be v by u, where u is the speed of rain. So this will be the correct. When you see that v is 0 when theta is 0, this is dimensionally correct as well. It is claimed that two cesium clocks, if allowed to run for 100 years free from any disturbances, may differ only about points. What does this imply for accuracy of the standard cesium clock in measuring a time interval of 1 second? In 100 years, there are how many seconds we have to calculate? Total seconds in 100 years is as follows. That is 60 into 60 into 3, 65.25 days in a year into 100 years into 24 hours. And this is 0.02. And difference is delta t is just 0.02 second in this time. If you divide it by this, you'll get 60 into 60 into 20, 365.25 into 100, dividing it by 0.02, you'll get a number between 10 to the power 11 to 10 to the power 12. So there is accuracy of 1 part in 10 to the power 11 to 10 to the power 12. We'll say accuracy of 1 part in 10 to the power 11 to 10 to the power 12, and so. Estimate the average mass density of a sodium atom, assuming its size to be about 2.5 angstrom. Use the known values of Avogadro number and the atomic mass of the sodium. Compare it with the density of sodium in its crystalline phase. that is equal to 970 kilogram per meter cube. Are the two densities of the same order of magnitude? If so, why? According to this, we have to find density, mass by volume of a sodium atom. While the mass of a sodium atom is equal to molar mass divided by Avogadro number. Molar mass is 23 10 to the power minus 3 kg, that is 23 gram per mole, and Avogadro number is 6.02 10 to the power 23. So with the help of this data, 23 into 10 to the power minus 3 kg divided by 6.02 into 10 to the power 23, we find the mass, and we have to divide it by volume as well. Volume will be 4 pi size of the sodium atom is 2.5 angstrom, so we'll use it here, 1.25 10 to the power minus 10 cube, because it is angstrom, and size is the size of the diameter, so I'm taking this value. Let us see this problem. The unit of length convenient on the nuclear scale is a Fermi. One Fermi is 10 to the power minus 15 meter. Nuclear sizes obey roughly the following empirical relation. R is R0 or 1 by 3, where R is the radius of the nucleus, A is the mass number, and R0 is a constant equal to about 1.2 Fermi. Show that the rule implies that nuclear mass density is nearly constant for all different nuclei. Estimate the mass density of sodium nucleus. Compare it with the average mass density of the sodium atom obtained in exercise 2.27. To find mass density, first we will prove that mass density is almost constant. Density is mass by volume, while mass is proportional to atomic mass number, and volume is 4 by 3 pi r cube. If we see that 4 by 3 pi r cube, we replace r naught cube with a, where a to the power 1 by 3 cube is a, so a and a cancel, and density comes out to be 3 by 4 pi r naught cube. This is independent of a, so we prove that density is constant. Here we'll see that mass is proportional to a, so we'll take a constant something like k here. That means the unit is now density. To find density in our proper unit, we have to find density of nucleus having one atomic mass number. That is, one atomic mass number is of the weight 1.67 into 10 to the power minus 27 kg with 4 by 3 pi r cube, and this is one atomic mass unit. If we use a, the k will be 1.67 10 to the power minus 27 kg. So you can find the atomic mass density here, nuclear density basically. So you'll find nuclear density here, 4 by 3 pi. So you will find nuclear mass density 4 by 3 pi r cube, that is r naught cube, because a is 1, so it will be 1.2 into 10 to the power minus 15 cube. It will comes out to be 0.3 into 10 to the power 18 kilogram per meter cube. If you compare it with the value obtained in 2.27, you will get it is 10 to the power 15 times more as compared to atomic mass density of the sodium. Let us see next problem. A laser is a light source of very intense monochromatic and unidirectional beam of light. These properties of a laser can be exploited to measure long distances. The distance of the moon from the earth has been already determined very precisely using a laser as a source of the light. A laser light beamed at the moon takes 2.56 seconds to return after the reflection at the moon's surface. There is a mirror placed by Apollo mission on the moon that reflects the laser beam to the earth. How much is the radius of the lunar orbit around the sun? You will find the average radius of the lunar orbit, and it takes 2.5 seconds to come back after the reflection at the moon's surface. So the distance is twice the radius, and it will be equal to 2.56 times the c, where c is speed of light, 3 into 10 to the power 8 meter per second. Then r will be simply 2.56 3 into 10 to the power 8 divided by 2 meter, and it will comes out to be 3.84 into 10 to the power 8 meter up to 3 significant digit. Let us see next problem. A sonar sound and ranging uses ultrasonic waves to detect and locate objects underwater. In a submarine equipped with a sonar, the time delay between generation of a probe wave and the reception of its echo after reflection from an enemy submarine is found to be 77 seconds. What is the distance of the enemy submarine? Speed of sound in water is 1450 meter per second. Here again, the distance will be simply speed of sound into time taken divided by 2, because it is the time taken in two-way journey of the sound. So it will be 1450 into 77 divided by 2, and it comes out to be 55.8 kilometer, and comes out to be 55.8 kilometer. Here we'll see another question. The farthest object in our universe discovered by modern astronomers are so distinct that light emitted by them takes billions of years to reach the earth. These objects, known as quasars, have many puzzling features which have not yet been satisfactorily explained. What is the distance in kilometer of a quasar from which light takes 3.0 billion years to reach us? 1 light year is equal to 9.46 into 10 to the power 15 meter. In a travel of 3 billion years, light will travel a distance of 3 billion means 10 to the power 9, and in 9.46 into 10 to the power 15, and the answer will be 2.8 into 10 to the power 25 meter. And this is the distance between Earth and the quasars. It is a well-known fact that during a total solar eclipse, the disk of the moon almost completely covers the disk of the sun. From this fact and from the information you can gather from the example 2.3 and 2.4, determine the approximate diameter of the moon. If you are on the earth and you are looking towards the solar eclipse, this is the diameter of the moon, and this is the sun, which covers almost all the rays from the sun. And here there will be a spot where you will see the total solar eclipse. This is the distance between moon and earth, and this is the distance between sun and earth. Example 2.4 gives us the information that this is about, this angle is theta subtended by the sun on the earth is 1920 seconds, while this distance is also given, that is equal to 1.496 into 10 to the power 11 meter, and let this is the diameter of the moon is d. Then d by dm, and this will be equal to angle theta, that is equal to 1920 second, but we have to convert it into the radian. Again, to convert seconds into radian, you have to divide it by 60, that will convert it to the minutes. Again divided by 60, it will convert it to the degrees, and multiply by pi by 180, it is now in the radians. To find diameter of the moon, it will be 1920 upon 60 into 180 into pi into diameter into distance of the moon from the earth, which is a result of example number 2.3, which gives that distance dm is equal to 3.84 into 10 to the power 8 meter. Calculating this, you'll find the required answer, that will be simply 3.581 kilometer. The calculation is not the problem at all. Problem is of the concepts that you use here. So it is very simple things in this first chapter. I will expect that you will do all the problems from IIT JEE and last year other engineering and medical entrance examination.